The national map is a collection of mapping products and services produced by the USGS National Geospatial Program. The products and services are accessed via the Internet through service calls and graphical user interfaces. The National Geospatial Program has released a series of how-to videos for people who are working with the national map data and services. The videos show how to use the services and interfaces to access data and tools for viewing, analyzing, and printing geospatial data. Lessons 1 and 2 serve as an introduction to the training materials, and the remaining how-to videos may be viewed as needed in any order, depending on the user.
Lesson 10G1: Importing and Visualizing Elevation Data using GRASS GIS. This lesson will show how to run GRASS GIS and utilize GRASS's unique user interface to import and visualize elevation data. Any use of trade, product, or firm names is for descriptive purposes only and does not imply endorsement by the U.S. government. By the end of this lesson, you will know how to initialize GRASS on your machine, understand the history of GRASS uses and capabilities, execute commands and import data into GRASS using the command console and module library, and apply various data visualization techniques to raster data. For this lesson, we will be using a dataset from El Paso County, Colorado. If you have not done so already, please download co_El-Paso_County_training_data.zip file from our Rocky website at https://rockweb.usgs.gov/training_data. This may take a few minutes to download. After you've downloaded the LiDAR data, extract the zip file into a folder on your local computer to use during the lesson. The National Map has a download client where you can find USGS products, including elevation data such as LiDAR point clouds, at https://apps.nationalmap.gov/downloader/##. If you are interested in learning more about downloading products on the National Map, be sure to check out our training videos located at https://www.usgs.gov/ngpvideos. GRASS, or Geographic Resources Analysis Support System, is a GIS developed for vector and raster data management, analysis, visualization, and geoprocessing. It is free and open to all users under the GNU General Public License. GRASS GIS was first developed in 1982 by the U.S. Army Corps of Engineers Construction Engineering Research Laboratory for environmental research and military land management purposes. The Open Source Geospatial Foundation adopted the software to develop and promote for worldwide use and collaborative development in the free and open source software for geospatial applications, or FOSS4G arena. GRASS is widely used as a main FOSS4G software that is free and available to any user for download. In this lesson, we will be using GRASS GIS version 8.2.0. If you do not have GRASS GIS already installed on your computer, you can download it at https://grass.osgo.org/download/. To begin, open GRASS GIS on your computer. Launch GRASS GIS. Once GRASS GIS is open, you should see the default database, GRASS Data. There are three parameters that need to be set up for a new project: the database directory, location, and mapset. GRASS is unique in that it requires the user to set up the environment and directory for each project. The first parameter is the GRASS GIS database directory. This database directory contains all projects organized by project areas. These project areas are stored in subdirectories called locations. Click the Add Existing or Create New Database button to specify the database directory. In the Browse pop-up window, navigate to the folder the zipped data was extracted to. Select the new extracted folder and click OK. We will need to make a new location or subdirectory in our database directory. These locations are defined by a coordinate system, map projection, and specific geographical boundaries. These geographic and projection files are automatically created for each location when GRASS is run for the first time for a new location. When selecting a new location for a new project area, you can select the projection and location from a drop-down list of EPSG codes, or you can use a geo-referenced file, like a GeoTIFF, to define the project area, projection, and map units. The EPSG code is a 4 to 5 digit number that identifies a specific coordinate reference system. This code can be found in the metadata if not already known by the user. The Define New GRASS Location dialog window pops up. The GIS database directory is displayed as the third parameter. For the name, it is a best practice to use a naming convention after the projection and units so that the location projection can be clearly identified and differentiated between projects. We have accessed the metadata in a contractor LiDAR collection report to specify the projection and datum for the GRASS project location. The data is in NAD 83 2011 Colorado State Plane Coordinate System FTUS. Type El Paso _ State Plane CO _ Central _ FT as the new location's name. Click Next. Now we must choose the method for creating a new location by either choosing the EPSG code of the spatial reference system if known, or by reading the projection and datum terms from a georeference data file. In this tutorial, we will manually select the EPSG code as specified in the contractor report. If choosing to read the projection from a georeferenced file, be careful to ensure the datum and projected coordinate system are the same for the project and data used in the project, or you will encounter datum and projection conflicts when running processing tools. By reading the contractor report metadata, we can easily search for the EPSG code for the projected LAS and DEM files. Make sure the Select CRS from a list by EPSG or description radio button is chosen, then click Next. Based on the contractor report, our data uses the coordinate reference system NAD 83 2011 Colorado State Plane Coordinate System FTUS. In the search bar of the Select CRS from a List window, type Colorado Central and hit Enter to search. The list shows all the EPSG codes that match the search criteria. Select EPSG code 6428 NAD 83 2011 Colorado Central FTUS from the list. Then click Next. Accept the default Option 1 from the Datum Transformation window and click OK. Then click Finish. A message window will give you a summary of your current GRASS database, location, and map set. Click OK on that window. A new subdirectory or location was just created under the name El Paso _state plane CO _central _FT in the Layer Manager window. Within each database and respective location, various maps, also known as mapsets, will be stored. Raster layers or raster maps created through analyses are automatically saved as data files and can be easily added to any new mapset without needing to save the mapset settings to a new file individually. The permanent mapset shown below is automatically created with each new location. Its role is to store all the core data which the owner is permitted to modify or remove. In other mapsets, the data will be copied from the permanent mapset folder to prevent any overwriting of the source data. We will create a new mapset for this project. Right-click the location, choose Create Mapset, and name the new mapset CO _SP _central _FT _Garden of the Gods. It is a good idea to keep a similar naming convention that specifies the coordinate reference system and location. Click OK and you will see the new mapset is added to your location. The GRASS GIS GUI is composed of 3 parts: the Layer Manager, Map Display Window, and the Module Dialog window. The Layer Manager includes the table of contents for data layers and provides an interactive graphical interface for managing and creating GRASS displays. The Map Display window contains a toolbar that can be docked or undocked. The display window shows the processing extent portrayed as a red box. This extent can be changed to match specific data extents or can be manually determined. This Map Display window also allows the user to insert map elements, zoom in and out, and transition from 2D to 3D views. The Module Dialog window enables running GRASS modules in the background. For more details on the specific toolbar icons and tool functionality, refer to this information page at https://grass.osgeo.org/manuals/wxgui.html. It is important to understand GRASS modules in order to import, derive, or analyze data in GRASS. GRASS functionality is enabled through these tools and modules. Here is a list of some of the module groups used in GRASS. There are many other module groups in GRASS, many of which contain further grouping and functions. These modules can be easily found by searching in the Tools tab on the bottom of the Layer Manager window. In the Tools tab, you can either search for a module group or specific module function. You can also use the module tree to manually sort through the list of modules and functions. We will search for a module that will import our data. With the Tools tab selected, type IN period in the search bar and hit Enter. Make sure to include the period after in to find the correct tool. Here we can see the location in the module tree for all functions that contain an in period in its grouping. Another helpful tip is to click on the specific function listed in the module tree above to show a brief tool description. At the bottom of the window, a description of the tool opens up. This can be useful in finding the appropriate tool from the list of functions. Double-click Import of Common Raster Formats, R.in.GDAL, function from the tree. The Functions dialog window pops up with many tabs and parameters. First, we will insert the required parameters as requested in the window. Browse to the downloaded data folder select DEM_LD31741380.TIFF. Name the output raster map DEM_LD31741380. The r.in.gdel function also allows the user to manipulate variables such as bands, projection, metadata, extent, and other optional variables. Click on the Optional tab at the top of the tab list in the window. Each optional parameter is associated with a letter or word as shown here. These letters can be used in the console when specifying the function and parameters if already known by the user. Lastly, each tool's window has a manual tab. Click on the Manual tab. Here we can become more familiar with the specific tool syntax, every parameter and flag, a description of the tool, as well as examples for how to utilize the tool in the console window. It is a good practice to read through the manual of the tool before running the tool. We will only use the required parameters previously specified to import the data. Return to the required tab and click Run. The tool window shows the progress of the tool. Close the tool window when the function is completed. The raster should automatically display on the Map Display window. If the raster is not displayed in the Map Display window, click on the Layers tab in the Layer Manager window to view the layers. Right-click on the DEM_LD31741380 layer and select Zoom to Selected Maps. The computation region is the extent where all processing and analysis will occur, and is assigned to the selected map set and will affect all open map displays. It is displayed as a red box, and when switching map displays, zoom back to that display's selected map to ensure the proper computational region is set. Change the computation region to match the DEM raster map by right-clicking the DEM_LD31741380 layer and select Set Computational Region from selected maps. The computation region will then match the raster map layer's extent in the Map Display window. To save the workspace, go to the Layer Manager window. Click on the File menu. Navigate to the Workspace menu and select Save in the drop-down menu. Save the GRASS workspace file in your data directory. Name the .gxw file grass_tutorial and click Save. Additionally, to open an existing GRASS GIS workspace, you can do so by going to the File menu, Workspace, and selecting the Open option from the drop-down. You can browse to the previously saved workspace that would be saved as a .gxw file. We will now learn how to change the symbology and create more visual effects using GRASS modules. In the Tools tab of the Layer Manager window, type Colors in the search box. Double-click on the Color table's r.colors function. In the Tool window, select the DEM_LD31741380 at CO_SP_central_FT_Garden of the Gods raster map layer under Map Display from the drop-down as the input for name of raster maps. Click on the Define tab. We will change the color parameter. Click on the Name of Color table drop-down arrow and choose Elevation from the list. Click on the Manual tab to determine other parameters available to change and briefly scroll through the parameters. For now, we will only change the color name. Click Run when you have finished reading the manual's flags and variables. After the tool runs, click Close. GRASS has the ability to convert a 2D raster map to a 3D raster map in the Map Display window. In the Map Display window, change the 2D view to 3D in the Map Display toolbar. The Layer Manager window will automatically open a 3D View tab. This tab contains subtabs to control the 3D view, data, appearance, and analysis. In the Control View tab, click and drag the ball to around the box to view the data from any cardinal direction perspective. To zoom in and out in the data, use the zoom tools on the Map Display window toolbar or use the perspective slider. You can also change the vertical exaggeration or zigzag on the right side of the window. In the Appearance tab, the light source position can be adjusted to any cardinal direction and angle using the height scale on the right and dragging the ball in the light source position box to a specific direction. Change the 3D view back to 2D. GRASS has the ability to open multiple map displays in one session. We will create a new display and add multiple rasters in one command to the display. In the Layer Manager window, click on the Start New Map Display icon located in the top left corner of the toolbar. A new Map Display window will pop up and the Layer Manager window will show an additional display tab, by default named Display 2. Notice the computational region in red in the Map Display window. This is the area in which all processing and analysis will occur. We will now add a list of all the rasters from the downloaded directory to the new display. With the Display 2 tab selected in the Layer Manager window tab, navigate to the File menu in the top left corner of the window. Select Import Raster Data from the drop-down list. This time, select Simplified Raster Import with Reprojection, also known as the r.import function. When the Tools window opens up, choose Directory for the source type. Double-check that the format is GeoTIFF with the extension TIF. Then click the Browse button and navigate to B_rasters folder. Highlight the folder and click Select Folder to put the data in the Download folder. This will pull all files ending in TIFF in the directory selected. After choosing the directory, there should be a total of 6 TIFF files that both match the projection of the project location and show the names of the DEMs that were downloaded. If they are not all selected, right-click the box next to the number 1 in the Layer ID column and choose Select All. Finally, check the box to allow output files to overwrite existing files. Click Import and close the tool window when the import is finished. The 6 DEM tiles should be added to Display 2. The computation region and display may not match the extent of all 6 raster tiles. In order to change the display to match the 6 raster maps, highlight all 6 DEMs in the Layer Manager list by left-clicking while holding the Shift or Control key. Right-click the highlighted layers and select Zoom to selected maps. Then, to set the computation region to match the entire dataset, right-click the selected 6 raster maps and select Set Computational Region for selected maps. The red box will match the extent of the selected data. With all 6 raster maps selected, right-click again and choose Set Color Table. This will open the same colors tool used previously, but will already load the 6 raster map layers into the input Name of Raster field. Click on the Define tab and choose Elevation from the Name of Color Table drop-down list. Then click Run and then close the tool. Now we will remove the layers and close the display window. To remove a layer from the Map Display window, navigate to the Layers tab in the Layer Manager window, if you have not done so already. Select all 6 DEM raster maps and right-click the layers. Select Remove from the list. Click Yes to remove the map layer. We will close Display 2. With the Display 2 tab selected in the Layer Manager window, click the X in the right corner of the green ribbon below the toolbar. Choose No if asked to store current settings to Workspace file. Now that we know a little bit about how many modules and functions are structured in GRASS, we will explore the Console tab in the Layer Manager window to verify the metadata and the processing environment of the project. Click on the Console tab. In the console input window at the bottom, begin typing r.info. You will see a drop-down list update as you type. You can either type the whole expression or choose the function from the list and hit Enter. This can be another useful way to search for tools by name. However, spelling and syntax must be correct. Once r.info is in the console input window, hit Enter again and the Tools window will pop up. In the name of raster map parameter, choose dem_LD31741380 from the mapset CO_SP_central_FT_Garden of the Gods list. Click the Manual tab to read about the flags and other variables helpful in determining information about the data. Once you have read over the syntax and tool description, click Run. The tool window shows the print statement in the command output generated by the tool. You can expand the size of this box if you cannot see all of the text. Here we can see the resolution is 2 feet, the total number of cells, and the extent, as well as the minimum and maximum elevation values in this DEM. Close the window when you have finished reading the raster's metadata. Now we will enter a command in the console to show the current processing settings using the region function. In the Layers tab, right-click the DEM and set computational region from selected maps. In the console, type g.region-p and hit Enter twice. This statement utilizes the General Region Processing Settings function and uses the -p flag to print the current processing settings. Here we can see the current output resolution for geoprocessing is 2 feet, or about 0.61 meters, as well as other useful metadata. Now that the processing resolution has been verified, we will generate shaded relief mapset for dem_LD31741380 in the current Map Display 1 window. Click the Clear button, then in the Console tab of the Layer Manager window, type r.relief and hit Enter twice. There are 2 required parameters, the input elevation map and the name of the output shaded relief map. The other optional parameters enable the sun angle and azimuth to change, as well as vertical exaggeration. Read the Manual tab for more information on the flags and parameters to be changed. In the name of input raster parameter, select dem_LD31741380 from the list. Name the output shaded relief map hillshade_31741380 and click Run, and then click Close. The hillshade relief raster map will be added on top of the display. To better visualize the results with color, we can drape the DEM over the hillshade and change the DEM opacity level. In the Layer Manager window, click on the Layers tab. Drag the DEM layer above the hillshade layer. Right-click the DEM raster map and select Change Opacity Level. Move the arrow to 50 and hit Apply and then OK. This method works well. However, there is another method that combines both rasters for a more robust result. Go to the Console tab and type d.shade. Hit Enter twice to open the tool window. The two required input parameters are the shaded raster map created from the r.relief command and the DEM to drape over the shaded relief raster map. Select hillshade _ 31741,380 for the name of shaded relief raster map and choose DEM _ LD 31741,380 for the name of raster to drape over the relief raster map. Click OK. Notice a new hillshade layer is shown in the display window and added to the Layer Manager layers list. It is important to note that the d.shade command does not generate an additional raster, so this layer is merely visual and cannot be used to perform analysis. A similar module, r.shade, will do the same function as d.shade, but will create a new output raster map. Save the changes by navigating to the File tab in the Layer Manager window. Under the Workspace drop-down, select Save. Congratulations, you finished Lesson 10G1, Importing and Visualizing Elevation Data using GRASS GIS. Close the Layer Manager window and select Quit GRASS GIS to close the program. In this lesson, we discussed how to initialize GRASS GIS and start a new GRASS session on your local machine, import raster data into GRASS, execute commands and functions from the Command Console and Module Library, as well as apply various visualization techniques for raster data. If you are interested in learning more about using various GIS software to explore and analyze elevation data, please see the additional USGS training videos on ArcGIS Pro, LP360, and Global Mapper at www.usgs.gov/ngp videos.